There we go. So now those are on the recording if you ever, well, not what I just said, but at least the stuff that's on the screen is on the recording. But now it's getting erased. So, oh, this is going to take me a while. I always forget. Erasing on here is terrible. There's no just like erase everything in this generic section. Don't mind me. All right. So last time we didn't quite finish this last problem here. So let me remind us what we were doing. Yes, I can. Doop, doop. Or maybe I can't. There we go. There we are. So a reminder of what this question was doing. Remember, we're doing these things that we call Riemann sums. So there are, kind of rectangle idea where we're estimating all of our areas with rectangles. So what we were given here in the problem that I'll scroll back down to in a second, we weren't given a table, which is what we've been working with most of the time. We were given a generic function. Now I created a table, but we weren't given a table. So you don't need a table as long as you're given a function. So what we had to do is we took, brain. We looked at the function we were considering, which was this 3 plus 0.1 t squared. We were to make an underestimate. Now, since it's an increasing function, an underestimate is going to be a left estimate. And again, I said this before, when I write a problem, I always say left or right. The book in Wiley likes to do the underestimate, overestimate thing. But remember, now I'm going to scroll back up to the thing I just scrolled down from. As long as it's increasing or decreasing purely on that interval, you can tell which one it is. You might need to think about it a little bit. But so since this was an increasing function and we wanted an underestimate, we had to use a left-hand side, which is essentially the third picture in this thing that's on the screen right now. So we needed a left-hand estimate. So we had to do it in 3 different ways. Well, we're not going to do the third one fully. We're just going to talk about it. But we needed to split it up into essentially sections of length width 4, sections of width 2, and then sections of width 1. So we had 5 rectangles in the first case, 10 rectangles in the second case, and we would have 20 rectangles in the third case. But again, we're not going to do that one out fully. So since I know I needed widths of 2 eventually, I went ahead and we found the table for widths of 2. And then for the first calculation we needed, since we wanted widths of 4, we only needed to use the values at 0, 4, 8, 12, 16, and 20. Well, not necessarily all of them because we were using a left-hand side, but those were the ones that we needed to consider. Which is why I wrote this down here, broke it up into our intervals 0 to 4, 4 to 8, 8 to 12, blah, blah. So we were using our left hand, so we just used the left hand points there. All right, so that was our recap. So now let's go on to finishing this problem. So now we want to calculate this underestimate using a change of t being 2. So remember, change in t, the delta t is the width. And if you see n equals in the homework, which I haven't assigned yet, that means the number of rectangles. So breathing. Since the width of all of our rectangles is 2, remember we can essentially write the width of the rectangle out on the very outside and then sum up the lengths, the heights. So we can go ahead and put 2 on the outside and then we just have to sum up all of the lengths. Let me go ahead and write out the interval notation in case anyone really likes that. So we're going from 0 to 2, 2 to 4, but it's going to take me a while, 4 to 6, 6 to 8, 8 to 12, 12 to 4, no, 8 to 10, 10 to 12, 12 to 14, 14 to 16, and 16 to 18, and 18 to 20. Which is why we're not doing the last one, because it would be twice as many as this one is. So since we want the left-hand side, we want to use the y values associated with all the left-hand endpoints. So 0, 2, 4, 6, 8, 10, 12, 14, 16, and 18. So we're essentially going to use all the values on our table except for the one at 20. So we'll have 3, 3.4, 4.6, 6.6, and so on. If you were to be doing this on a test, although I don't think I would ask you to do both of them because I know they get super tedious, if you had the table, you could totally, if you had the table, you could totally write something like 3 plus 3.4 plus ... plus 34.4. I do need to see the values somewhere. So if you had the table, you could totally like do that kind of skip notation. If you didn't have a table, you would have to write it all out. But anyway, so this is going to be our underestimate for essentially using 10 rectangles. So delta T would be 2. And remember, we were getting that because we were asked to work over a 20-hour period. So breaking 20 hours into, sets of 2, you get 10 sets of 2 essentially. So plug that sucker into a calculator. You get, where is it in my notes? 288. Now, in terms of a quiz or an exam or something like that, I doubt I would even ask you to do 10 pieces, but 10 pieces is the maximum I would ever ask you to do. So this problem that we just wrote out here would be the longest I would ever ask you to do. I usually ask you to do less than that because I know that you can show me that you know what you're doing without having to do 10 pieces. But like this third piece of this question, which we're just going to talk about, oh, because I wrote it down wrong, Kayla. That's a 35.4, ain't it? Can't read my own gosh darn table. Sorry. 35.4, not 34.4. My answer should still be right because I pulled it off my notes, but sorry about that. What was I rambling about? Oh yeah. So I won't necessarily ask you to do one that has 10 pieces. That would be the maximum. But this part 3 that we're just going to talk about, that would technically have 20 pieces. So we would need to find f of 0, f of 1, f of 2, f of 3, f of 4, f of 5, f of 6, f of 7, f of 8, and so on and so forth, which is 20 pieces, which is a lot. And it's too many for me to ask you to do. I know they get tedious, and I wouldn't want to write out 20 pieces, so I'm not going to ask you to write out 20 pieces. Yeah. So just talking about this last one. I kind of talked about it already, but in full generality, if we were to do this third one, which again, we're not actually going to do full out, but if we were to do this one, we would essentially need a width of 1, and we'd need to find f of 0, f of 1, f of 2, and we'd have to go all the way up to f of 19. So let me write the last two terms, f of 18 plus f of 19. And we stop at 19 because, again, we have the 20 intervals, but the left-hand endpoint of the last interval would be 19. So we stop at f of 19. So we would need to find all of those values that we didn't have already and plug them in. If you're curious, this is 307. So notice that these values don't match. Right now, I know we found one of them the other day, but we found 252 the other day, and we found 288 right now, and I just told us that this last one was 307. So now that kind of makes sense that those values are increasing because this is an underestimate. So the better the estimate gets, the larger it should actually be, because we should be underestimating it less, if you will. Now, also, if you're curious what the actual full answer would be for, like, so remember, we're trying to calculate area underneath of a function. If we were to find the actual area for this function, it would be, so the actual area, and we'll learn how to do this soon. So the actual area would be 326.67 approximately. Once my screen catches up to me. So if you notice, our first estimate of 252 is actually pretty far off. It's almost 100 units off, and we get better the larger amount of rectangles we take. Now, of course, the more rectangles we take, the more tedious the question becomes, but the more rectangles we can take, the better. And that's kind of what we're going to lead into with 5.2, which we're going to start in about a hot second. But I'll wait and I'll see if anyone has any questions about what we just did. And then we'll jump over to 5.2. So we'll wait like 5 seconds and drink some tea. Okay. Oh darn, I don't think I actually officially pulled up 5.2. I'm not ready for my own class. Here we go. All right, now 5.2, and I'll switch over to the screen in a second. 5.2 is a weird section. Possibly, Kayla. 5.2 isn't a very long section, so if we get through 5.2, I can probably catch some questions at the end. But let's go ahead and get 5.2 under. So what was I saying? 5.2 is a weird section because the main point of it is just setting up a definition. So we don't do a lot with the material in 5.2, but get a definition out of it. You'll kind of see what I mean. So we kind of need to take a side note first. So 5.2 is about this thing called the definite integral, but we've got to take a side note because we have to get some notation to be able to define the definite integral. So we have to talk about this thing called sigma notation first. So sigma notation enables us to write a sum that has many terms in a compact form. So that's a very great way for my camera to stop there. All right, cool. So we were just writing out these really obnoxiously long sums on that last question, right? So sigma notation is a way to write them really condensed, and this is what it looks like. And I know it can be kind of freaky for people who don't like math, but it's going to be okay. So essentially, what I just wrote is the sigma notation. So that big E-ish looking thing is a sigma, if you didn't already know that. So what a sigma notation essentially does is it takes something, and the sum has to be very specific. It has to be something that's like all of the terms have to have something in common. So sigma notation would be used for like writing the sum of all even numbers, all odd numbers, all squared numbers. You know, they have to have something in common between each term. Because essentially this thing right here is essentially what tells you what each term is going to look like. And we're essentially saying, okay, to start off, we're going to plug in 1, and that's going to be our first term. So if I plug in a 1 where I see a k, I would get x sub 1. Now, of course, in this generic notation, we don't really know what x sub 1 is. It doesn't really help us very much, but that's what we would do. And then we essentially keep using natural numbers, or the positive integers, if you like. And we keep going until we get to this number on the top. Now that's a generic number n, so we're just going to write n there. And we'll see an actual numeric example in a second. Yes, I can. But that's kind of what sigma notation does, is it takes a very generic looking term and you plug in natural numbers to it until you get to the number at the top. Someone raised their hand and then dropped it. Maybe it was because you wanted me to share my screen. But if not, let me know. Oh, my one screen is freaking out. Oh, it's really freaking out. Oh, it's better now. So I think it'll make a bit more sense when we do one with actual numbers in a second. So that Greek letter sigma stands for sum, which is why we use it here. That's kind of, they made it so that it worked like that. Now, the index of summation. And that's the k, is going to tell us where the sum begins and where it ends. So in the generic one above, it starts at 1 and it ends at n. Now, any number can be used to denote that index. It doesn't have to be k. Usually I, j, and k are customary to use there, but technically those variables don't matter. That could be I equals 1, it could be j equals 1, it could be a equals 1. But usually I, j, and k are used more often than not. So for instance, say I wanted to write out, 1 plus 2 plus 3 plus 4 plus 5. The first 5 numbers added together. Well, we would write that in sigma notation. So essentially, we're just taking that generic number. We're not doing anything to it. So we would say something like k, where k starts at 1 and ends at 5. So this is telling me to add things together that look like some k. Like it's not 2 times k, it's not k squared, it's just that value. And this tells me start with 1 and go up the natural numbers, positive integers, until you hit 5. So this would be telling me to add 1 and then 2 and then 3 and then 4 and then 5 together. So let me write one out and try to go the other way. If I had something like, let's do k squared, let's do 2k, where k equals 1 to 4. Let's not go too far because I'm going to run out of space. So if I wanted to expand this out, I start at 1. So I let that k value be 1. So we'd essentially have 2 times 1. And then I keep going until I get to 4. So 2 times 2 plus 2, 3 plus 2 times 4. And of course you could simplify them along the way, but just to kind of stress the notation out, that's how that would work. Now again, a lot of this in 5.2 is just to build up a definition. So we're not going to do a ton with sigma notation. It's just so that you can understand a definition that we're going to get to in a second. But say we did want to do one example of sigma notation. We want to express the sum 1 plus 3 plus 5 plus 7 plus 9 in sigma notation. So the first thing, so we essentially need to find, where we're starting, where we're ending, and the kind of common pattern between all of the terms. So notice that all of these terms, 1, 3, 5, 7, and 9, are all odd. They're all odd terms. And I don't know if any of you would have seen this before in your life, but there is a specific way we can write absolutely any odd number. And that's any odd number is going to take the form 2k minus 1 for some k. So essentially any integer, so maybe I should be very specific in case people show this to other mathematicians later, for any integer k. So if you give me an integer, if I plug it into 2k minus 1, I'm going to get an odd number. No matter what integer you give me. If you give me 0, I'm going to get -1, which is odd. If you give me 1, I'm going to get 1, which is odd. If you give me 2, I'm going to get 4 minus 1, which is 3, which is odd. Any integer you give me, if I plug it into that thing, I'm going to get an odd number. So essentially, since all of those numbers are odd, they all take the form of some 2k minus 1. So that's kind of going to be our pattern between all of the numbers, is that they can be written as 2k minus 1 because they're odd. If you're wondering why that's a thing, it's literally the definition of an odd number, is that it can be written as 2k minus 1. It's not a definition that a lot of people see, but it's technically the definition of an odd number. Now, this sum starts at 1. So what k value do I have to plug in there to get +1? I would have to plug in +1. So we'd have to say this starts at k equals 1. And then we have to go all the way up to 9. So what k value do I have to plug in to get a result of 9? What do I have to plug into 2k minus 1 to get 9? So I'd essentially need 10 minus 1. So we would need to plug in 5. So we need to go all the way up to 5. So this sigma notation here is exactly 1 plus 3 plus 5 plus 7 plus 9. Because it's 2, 1 minus 1 plus 2, 2 minus 1 plus 2, 3 minus 1 plus 2, 4 minus 1 plus 2, 5 minus 1. So that top number is telling us when to stop, because if there wasn't a number there, we would keep going forever and forever. So the last number we have in this sum is 9. So if I want to say that 9 is written as 2k minus 1, let me kind of come off to the side. If I want to write 9 as 2k minus 1, it's lagging a little bit for me, Sam. I've been keeping up, but if it lags more on your side, just let me know when you need me to slow down a little bit, and I'll slow down. But Sarah, if I want to write 9 as 2k minus 1, then if you can actually kind of solve this algebraically. Add 1 to the other side, you get 10 equals 2k, and then k equals 5. So essentially the last number, since the last number we want is 9, and that's going to happen when I plug in 5, that's where I need to stop. So since that's where I need to stop, that's why the 5 goes on top. So the actual answer to this question, J, would be this sigma notation over here. Benji, it sounds like a sassy answer, but it's because it's the definition of an odd number. Any odd number can be written as 2k minus 1. Now, again, since we're not going to do a ton with the sigma notation, you don't really need to worry about knowing that. Kind of trust and believe me that any odd number can be written as 2k minus 1. But that's kind of what it means to be an odd number. So essentially, the definition of an even number, the definition of an even number is that can be written as some 2k, and the definition of an odd number is that it can be written as 1. Let's catch up with me, screen. So the fact that they're all odd numbers and the fact that the definition of an odd number is that it can be written as 2k minus 1 is where I'm getting that 2k minus 1 from. The main thing you should be understanding from this question is how the sigma notation relates to that sum. Okay, again, we're not doing a huge amount with sigma notation. You just need to understand it enough to understand the definition we're going to say right in a second. So if you can kind of follow how that gives me that sum, you'll be all right. But yeah. Any more questions on that one before we move on? Okay. So we're essentially at the definition that we needed that sigma notation idea to build up to. Now, I will say that this is probably one of the grosser looking definitions we'll ever see. So if you ever want to freak anybody out, just give them the definition of a definite integral. So suppose we have a continuous function, which again, all functions that we work with are continuous. 98% of all functions we work with are continuous, and you don't really need to worry about the non-continuous for this case. Anyway, so suppose we have a continuous function on some interval, then the definite integral of f, some function, from a to b is the same way. Kind of squished, fancy looking s, a to b, f of x, dx. Now, the a and b are what we're going to call our bounds, and the f of x is what we're going to call the integrand. So if I say integrand, I'm referring to that function, and if I talk about bounds, I'm referring to those are going to be numbers, but the numbers we're working with kind of on the bottom and the top of that integral symbol. So that kind of squished s is an integral symbol. So this is defined to be the limit of the left hand and right hand sums, so the Riemann sums we were just working with n subdivisions of that interval as n gets arbitrarily large. Now this is where the scary notation comes in. Don't panic, it's just a definition. In other words, if x sub 0 through x sub n are the endpoints of a subdivision, we define the integral, and I'll draw a picture in a second, to be the limit as n gets arbitrarily large Now this sigma notation, whoops. Again, this is just a definition. Don't panic. It's a definition. Don't panic. I know it looks super gross, but let me explain it in a second. I just need to write out the actual definition. Don't panic. Okay, let me explain this definition. These things right here. These things right here, the sigma notation stuff, those are your Riemann sums. They're just written that way. So if you think about that example we started with, we had this really obnoxiously long sum. They're essentially saying, let's just write it in sigma notation. So just trust and believe that that's a Riemann sum. So those two scary looking things on the right are Riemann sums, okay? So here's what this definition is trying to say. Let me draw a picture and try to, those are all I's. Sorry, do some of them look like semicolons? They should all be I's. So say I have some function. So think about what the Riemann sum is doing. The Riemann sum is taking it and it's breaking it up into, you know, these subintervals, right? And this definition is calling those subintervals x sub 0 through x sub 1, x sub 2, and so on. So that's what those mean. That's essentially just where you're breaking it up over that interval. Now think about this. Again, this is just making you understand why this definition is what it is. So what that definition is saying is that, so n is the number of rectangles, right? That's going to be the number of rectangles here. N is how many rectangles we have. So this is essentially saying take infinitely many rectangles. Okay? So infinitely many rectangles would get us the total area underneath of that function, not an overestimate, not an underestimate, the perfect amount of area. If we could somehow take infinitely many rectangles. Now, I know that's not physically possible, but that's what this definition is saying if you can take infinitely many rectangles, you have the actual area, let's call it an integral. So they're saying, if we can calculate this integral thing, which we'll find a way to do it in a day or so, if we can calculate this integral thing that we're saying is equal to this nasty sum, then we have the full area. That's all this is saying. It's saying if we take a Riemann sum with an obnoxious amount of rectangles, we've got the area. It just looks really scary. Okay, so don't panic. I swear this is not as obnoxious as it looks. Well, it's obnoxious, but it's not as hard as it looks, I promise. Maybe I shouldn't promise that, but now I'm getting nervous because I'm just talking to a screen and babbling. Okay, anyway, we've got this scary notation to just say if we could take infinitely many rectangles, we could find the area. So we have this new notation for this thing called an integral. So consider the example that we looked at last time. It's actually the one that we just started with at the beginning of class. T was in hours since that 20-hour period, and we had that the bacteria population was increasing by that rate of 3 plus 0.1 t squared. So if I wanted to write the result that we were looking for as a integral, what we would have been looking for is we wanted the total area between 0 and 20, right? So we would have wanted the integral from 0 to 20 of that function, which is how I actually went and calculated the actual area. So at the very end, I said, if you're curious, the actual area is blah, 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 blah. And the way I found that is that I calculated this really quick in my calculator. Now, one other thing that I haven't said yet, this thing back here, it was written as a dx above. The variable just matches the variable that's in the function that you're using. So since we have a t squared, it's dt instead of dx. That's just notation. Like, it has to be there, but you can almost kind of ignore it. In terms of our class, it gets important later in different calculuses. But anyway, in terms of our class, it doesn't really do anything. It just tells us what variable we're working with. So that dt, while it has to be there, doesn't really do much. but that's how we would represent the actual area underneath of that function between 0 and 20. And that's all I wanted for that question. Now, we're almost done. Well, maybe. Now, I'm going to tell you how to do this in your calculator. We are going to do them by hand. Trust and believe. We will be doing them by hand. But I will tell you how to do them in your calculator. Now, if you have a different calculator besides a TI-8384 or a TI Inspire, email me. I'll probably have to Google it. But let's, can I pull up my, I should have pulled this up already. Should have had it up already. So, whoops, that's not what I want. So say I want to put this in my calculator. I'm trying to pull out my calculator thing. One moment, please. So say we want to calculate the one we just wrote down. So, well, now I'm going to unshare my screen, so I don't know what I was really going for there, because I want to come over, where'd it go? Where'd it go? Oh. So, if you have a TI-83 or 84, you will do this. Now, if you have an older calculator, it's going to look grosser, and I don't know. Can I do an older version? No, it's only got the newer versions on here, but I'll explain what it looks like with an older version in a second. So say we wanted to calculate that thing that we just wrote down, that 3 plus 0.1x squared to the, well, t squared from 0 to 20. So what you're going to do is you're going to hit the math button, which is right below the alpha. Now you can either scroll down to number 9, or you can just hit number 9 on your calculator. So if I hit 9, if you have a newer calculator, it's going to come out looking like this. If you have an older calculator, I'll tell you how to do it in a second. So if it's a newer calculator, it's kind of nice because it just kind of sets it up for you. You just got to plug things into the right spot. So if we wanted to go from 0, and then I have to click the up button to get to the, well, maybe you can click the right button, I forget. Yeah, so you can either click the up button or the right button to get up to the next part. Ooh, it's lagging a little bit. And then so our top bound was 20. Press the right arrow key to go over to that middle piece. So our function was 3 plus 0.1. Hit the math button and then number 9. Math and then the number 9. So the math button is right underneath the alpha. But if you hit math, is there a way to? Yeah, so hit the math button and then number 9. So math number 9. Now for the variable, you always want to use this button directly under the mode button. So the second button down in that second column is the x, t, theta, n button. No matter what variable your equation has, just hit that button. I know it's an x and the original one was a t, but we don't care. And then it was squared. And then you have to scroll over to that last piece with the right button, hit that variable button again, and then just hit enter to solve it. Okay, so math 9, and these are, the instructions are on the notes too. So math 9, and if you have the newer one, it's kind of nice because it just lays it out for you. If you have an older version, I don't have a fancy thing to show you how to do, whoa, I didn't know that was a thing. Because yeah, it seems like they only have TI-84 Plus, which is still a newer version. But, so let me unshare this really quick. Well, I'm not going to come back to it. If you have an older calculator, you still hit math 9. You still hit math 9, but then it comes up with FN int and then blank. And so what you're going to need to do, if you were to do the one that we just typed in for the newer version, 60.2. That's not good. 1 second. So if you have an older calculator, if we wanted to do the one we were just doing, it would give you Fn int 86.6. Oh no. We'll have to fix that in a second. So you want to put the function that you want to integrate. So in this case, it was the 3 plus 0.1, and then you'll hit the X button still, squared. Gwen, that's what you should get. And then a comma, and then the variable button again. And then you plug in your bounds. So our bounds were from 0 to 20. Okay. So if you have an older calculator, an older 84 or an 83, that's how you'll do it. Oh, I forgot to talk about TI Nspire. For TI Nspire, hopefully my notes are right on this because I forgot to check. Wait, how do you get to the? So for that, you will you'll hit the menu button. You'll scroll down to calculus. X shouldn't be saved as anything, and I think that's the main issue, Benji. I'll talk about that in just a second. So you scroll down to calculus if you have a TI Nspire, and then there's an option for integral. It might say at a point. So you go down to that one, integral, and then just like with the newer version of the TI-84, it kind of sets it up for you, and you just got to plug things into the right spot. For people who did not get 326.6 repeating, here's probably what happened. So nope, not that either. So let me go back to that calculator thing really quick, and I'll come back to the notes in a second for anyone who's looking at that. When you need to put the X in there, you need to press. How can I like highlight it somehow? You need to press this. It's highlighted in red now. The XT theta N button, and that should just be, well, if you just put that by itself, it'll give you 0 or maybe, hopefully not something else. You do not want to use the X button from AlphaStow. So you can also hit AlphaStow to get NX. That you don't want that one. You must hit the XT theta N button. Otherwise, it's going to give you the wrong answer because you probably have something stowed in for X when you shouldn't. So math. Let's see this one. So clear your screen if you're trying to. If you didn't get the right one, clear the screen. Let's do it from scratch. So math. 9. I really hate doing this on a screen. Usually I can just walk over to you and see what went wrong. But, I didn't actually calculate that yet, Kayla, so I don't know. Then you want to do 0, scroll up 20 to 0, scroll over. The function was 3 plus 0.1 t squared, so 3 plus 0.1. Press the button directly under mode. There's no other way you should be writing an X in there. I know the original function was a T. You don't want to put a T in there. You want to use this XT delta theta N button. We got to square it. Got to scroll over. And once again, hit the... You still got 62. That's not good. Benji, you're usually in class on Wednesdays. I'm going to need to look at it. Without seeing what's going on, I unfortunately don't know what's wrong. Is there anything in mode that would do that? I don't think anything in mode changes any of that. So yeah, Benji, let me see it on Wednesday, and I'll try to figure out what went wrong. Because seriously, without seeing your calculator in front of my face, I literally don't know what else could have gone wrong besides hitting the wrong button. But we'll figure it out. We won't need it for a little bit, so we'll figure it out. Something else. So yeah, so let me do this, and we'll do this over here and this over here. And okay, apparently that can't get any smaller. That's obnoxious. Can I make something go away? No, I can't. Oh, no, I want that. There we go, that makes it a little better. Okay, so if you're having problems with your calculator, you won't be able to do the next one, but we'll figure it out. Again, also, if you have a different calculator besides TI-84, 85, 83, or an Inspire, we'll need to figure it out via Google because I don't know how to do it on any of the other ones. Let's say we want to compute the integral from 0 to 1 of e to the t squared dt. So we can do that by hitting math. 9, 0 to 1. So even if your calculator's not working, try again. Maybe magically this one will work. Probably not if it didn't work before, but just in case. So 0 to 1. And so let me remember, if you have an older calculator, you'll have to put the function in first. So the e to the t squared, comma x, comma 0 to 1. I'll write that out in a second. So our function, we need the e button, which is above the division sign. So you hit second division, second divide, caret, the x variable button, caret 2, or you could hit the square button if you wanted. Scroll down a bunch, scroll to the right a bunch until you get over here, hit the variable button again. You get 1.46 blah, 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 blah. So if you have an older calculator, what you would want to put in is the following. And I guess we'll probably just stop here. So fn int, you'll put the, ooh, if you have an old calculator, you also need to be careful because it doesn't do the fancy thing where it pops it up into an exponent. So whenever you want to do exponents, put them in parentheses. And then you'll want to do, whoops, that'll be an x, because you'll use the variable button, comma, variable button, 0 to 1, which gives you 1.46, blah, blah, blah. And again, TI, Inspire, menu, calculus, integral, and then it kind of sets the format up for you. So you'll just use the arrow keys to get from one piece to the next. I can't even use my own Inspire, good Lord. And for the Inspire, it doesn't matter what variable you use. I usually just default to X anyway, but the Inspire is nice because if you wanted to put in T and T in both places, so you wanted to use T squared and then DT, the Inspire can handle that. So you would just use the keyboard at the bottom of the Inspire to write the T, but the Inspire can handle the different variable as opposed to the other one. So, if your calculator wasn't working and you're a person who comes to class usually on Wednesday, grab me really quick on Wednesday and I'll try to look at it. If you usually don't come to class, email me and we'll try to work something out. So I don't think it's worth going through these last two right now, so we'll go through those next time. So this is what I meant by 5.2 is a very weird section. It essentially builds up the definition of this definite integral. We go over how to find it in our calculator. We'll do these two kind of generic examples, which don't actually use our calculator, so you still have to remember how to do them by hand. We'll go over those on Wednesday. So in terms of your quiz, so we don't have a ton of time, but Kayla, I do have a little bit of time before my next class that I can stick around. Anyway, your quiz on Wednesday is going to be on Riemann sums. So 5.1. So Riemann sums. The camera froze. So quiz on Wednesday will be on 5.1 Riemann sums. So given a table or a function. Find right-hand side and left-hand side sums. So similar to the thing we started at the beginning of class with. Again, I won't ask you to do 10 pieces. I usually stop at around 5 or 6 as my max. But that'll be kind of the deal. I'll either give you a table or give you a function and ask you to find a left-hand or a right-hand sum. It's possible that I could ask you to find both and then average them. I will be very specific if I want those things. But that's what your quiz will be on. It'll be on Riemann sums. We'll finish 5-2 probably pretty quickly, and we might start 6-2 on Wednesday, which is essentially how to do these by hand without our calculator. So hooray! But we are out of time. If you have any questions, feel free to stick around for a little bit. I have a little bit of time before my next class. Otherwise, have a great day, and I'll see you on Wednesday. I'm going to stop recording.